There we go. Patrick the puppy goes wandering around his neighborhood as seen below. So he leaves the front porch. He goes north for a while. He stops. He goes to the right for a while, or east. He stops. In fact, you know what? Let's draw a little compass on here somewhere like that. A little compass rose. Okay? He eventually ends up right here. He doesn't take the shortest path to get there, but that's where he eventually ends up. Notice a series of arrows drawn on the map of a physics teacher's front lawn. Each arrow shows the magnitude, size, and direction of a series of successive trips made by Patrick the puppy. These arrows, showing both magnitude and direction of Patrick's displacement, are called vectors. When Patrick reaches his final spot near the car door, how far has he walked since he left the front porch? Diana, it really depends on what you mean by how far. What distance has he traveled? Well, the distance that he's traveled is that, plus that, plus that, plus that, because distance is a scalar. The distance would be 3 plus 2 plus 4 plus 4 plus 2 plus 2. It would be the length of each little path. What distance did he travel? Oh, plus 4 at the end. What did I write? A plus 2? Sheesh. Let's at least get the distance right, Mr. Dueck. 3, 2, 4, 4, 2, 4. Really, it's 5 plus 8, 13, plus 2, 15, plus 4, 19? 19 meters. What about Patrick's displacement? Displacement, all it cares about is what's your change in position. Where were you? Where are you? And to figure that out, we could draw a little triangle up here. How could we figure out how long this arrow is? It begins with the letter P and rhymes with Pythagoras. Really? Pythagoras. I thought I was being a little obvious. Too subtle? Ronnie, how long is this little side right here? How long is this side right here? Okay, can you go a squared plus b squared equals c squared? What's the magnitude of his displacement? And I think it works out evenly. 5 meters. We're not done though. That's only the magnitude of his displacement. A displacement also has a direction. What direction would we say? He started here. He went that way. We would write this as, we put an @ symbol, 53 degrees east of north. Because for me to draw that, I would start out like this and I would tilt east of north. Not north of east. North of east would start out going east and then go up that way. If you said 37 degrees north of east, I would take that because that's what that smaller lower angle is. But east of north. And we're going to practice the notation and the naming. So if you're a bit kind of, we're going to do a bunch. By the way, there are 2 ways to indicate that something is a vector. In diagrams or handwritten notes, we put a small arrow above it. So I would say that's displacement. No arrow on top, distance. In a textbook, they tend to either italicize or bold italicize. But since that's really hard to do in handwriting, we'll use the little arrow on top. In a textbook, if only the magnitude of the vector is important, the symbol plain italics is often used. Or they may use this. What do those 2 vertical lines mean, pre-calc students? Absolute value, which is really just how big, because you chuck the negative or any direction. I'll almost always clearly say direction only, or magnitude and direction, or magnitude only, when I ask you a question. Scalars and vectors. If you add 3 kilograms of sugar to 2 kilograms of sugar, you'll have 5 kilograms of sugar. Mass is a scalar. If you had 3 liters of water to 2 liters of water, you know what? You'd have 5 liters of water. Volume is a scalar. Scalar quantities have magnitude, but no direction. Other scalar quantities, hey, what are some things that we've learned this year that are scalars? Time. What else? Speed. Distance, right? Not displacement, distance. Especially next year in Physics 12, those of you that take it, one of the first things I'm always going to do whenever I introduce something new to you is tell you whether it's a scalar or a vector, because that's going to completely influence, Haley, how we're going to deal with it mathematically in the real world, in the physics world. Displacements are scalars. If I add 3 meters to 2 meters, I can get 5 meters. If I add 3 meters right to 2 meters left, I get 1 meter right. Or if I add 3 meters right to 2 meters up, I can get kind of a little diagonally at an angle different length. I can get any distance between 5 and 1. Any length, any magnitude between 5 and 1 at a bunch of different angles. So, figure 5.3, these two displacement vectors right here have been added with the rules for vector addition, which I'm going to give you in a second. As you can see, the resultant displacement, which is 3.6, it depends on the directions as well as their magnitudes. If I had this 2 pointing down, I'd get a displacement of 3.6 pointing down. If I had this 2 pointing slightly backwards, I'd get a very different displacement, shorter. In addition to displacements, what are some other vector quantities that we know of? Ben, velocity. What else? Acceleration is a vector, although we're kind of sloppy with that one, but yeah. What else? Momentum. Force. Lots of them. Displacement, we already said. Torque, Physics 12. Magnetic field, electric field, those are all Physics 12, but they're all vectors. So suppose I have two force vectors of 7 newtons and 5 newtons. What's the maximum force that I could possibly get if I have a 7 newton force and a 5 newton force and I want to combine them on the same object? 11. What's the minimum magnitude force that I could possibly get? 3. That's if you're same line or opposite lines. Anything else, any other angle between them, it's going to be somewhere in between 3 and 11. You already technically know how to add vectors in one dimension. If I add 5 meters east to 3 meters east, what is my displacement? Well, I said magnitude, I agree with you, but if I'm magnitude only, I'm going to say the biggest magnitude of a force would be 3, whether it's negative in the opposite direction or positive. I'm not going to be fussy on direction right now. Yeah, good question. How would I add 5 meters east to 3 meters east? I'm going to gulp. And since there's a compass on this page and I've turned the page, I'm going to do that too. It's going to be 5 plus 3. If you go 5 meters east plus 3 meters east, what is your final displacement? Magnitude. 8 meters. Direction. East. I think that one you already knew. And in fact, you're even okay on example 3. If I have a force 6.2 newtons to the left, and I combine it with a force of 6.7 newtons to the right, what's my resultant force? 0.5 newtons. Magnitude. Direction. Right. In fact, we're doing winner minus loser, which is why I snuck that in earlier this year. The third vector represents the sum of the first two vectors, and it is called the resultant. Now, Sean, here's the new stuff. The nerdy stuff. Adding vectors in 2 dimensions. Well, we represent vectors with arrows, and one way of adding vectors would be to very carefully draw them to scale using graph paper, a ruler, and a protractor, and then carefully measure the distance between them on the graph paper and take our protractor and find the angle, what degrees north, south, east, or west of what. Ugh. So here's the question we want to ask. If John travels 5 kilometers west and then 8 kilometers north, what's his resulting displacement? We could draw it, or better yet, we could use trig. How do we add vectors together? Ben, here is the rule. To add 2 vectors, we draw them tip to tail. Say what? Next page, example 4. Let's try example 4 here. What were the 2 vectors from example 4? What did we want to add together? Okay, I've turned the page, so I'm going to put a compass on here. What'd you say? 5 kilometers west? I'm going to draw that like that. Plus 8 kilometers north, I'll draw like that, and I drew it a little longer than the 5, roughly to scale-ish. How do I add 2 vectors? I draw them tip to tail. I draw the first one, 5, there's the tip. I start with the second tail right there, 8. And then it says the resultant, often we use the letter R with the vector sign for resultant, is the line from the tail of the first vector to the tip of the second vector. From the tail of the first, yoink, to the tip of the second, that's R. Thankfully, that's a lovely right angle, which means I can find the magnitude of R. R squared is going to be 8 squared plus 5 squared. What's the magnitude of the resulting, is it a force? Displacement. Can you go 8 squared plus 5 squared equals square root? And give it to me to 2 decimal places, let's say. 9.43 rounded off properly? Yeah. Meters, kilometers, right? That's the magnitude at direction. Okay. You see that red vector that we drew, vector resultant R? Where it starts from, this is the angle I'm going to find for the direction, where it begins, not where it ends, where it starts from. How can I find out how big this angle is? Well, this 8, opposite, adjacent, or hypotenuse. This 5, Which trig function, Jaren, has the O and the A in it? Thank you, Kemi. Did you know it? I thought she whispered it to you. Good? Okay. Nice. Tangent. What always goes next to the trig function? The angle. What's the angle this time? It's a variable. Which variable do we traditionally use for an angle? Theta. It's a shorthand way of saying, hey, we're doing trig. Equals a Kemi what over what? How would I find what angle has a tangent of 8 over 5? Ah, this is the second function. Can you find angle theta for me, please? Theta is going to be the inverse tangent of 8 over 5. It's going to be the... Make sure I'm in degrees, Mr. Dueck. Am I? I am. Inverse tangent of bracket 8 over 5. You get 58 degrees. So let's go back to where my answer is sitting. 58 degrees. That's only part of the direction. That tells me an angle. What of what? North of south, east of west, what of what? Well, look at how I drew my little vector, my little arrow. We started out going this way, and then we went that way. Which way did we start out going? And then we went of west. North of west. North of west. By the way, Rob, you could also have drawn the 8 first and then the 5. You could have gone tip to tail here. You would get the same magnitude, but you would get 90 minus 58, 32 degrees west of north, and I would take both answers. It's more than one answer each time. Depends on where you started drawing yours and whether you decided you were going to go east or west first and then north, north of west, or whether you're going to go north first and then west. Example 5. How do we add two vectors together? Draw them how? Tip to tail. How do we add two vectors together? Draw them how, Chelsea? To tail. How do we add two vectors together? Draw them how, Liam? How do we add two vectors together? Draw them how, Jaren? Sean, how do we add two vectors together? Draw them. Tip to tail. Okay? I'm going to be flogging that theme to death. Ready? Okay, now we can answer the question that we posed when we were pushing Taylor. Force 1 is 10 newtons due east. Force 2 is 6 newtons due south. When you combine them, what do you get? Magnitude and direction what of what? Let's see. I'm drawing a compass because I've moved down. There's force 1, 10 newtons due east. Plus, yoink, 6 newtons due south. Haley, how do I add two vectors together? Draw them. So if I'm going to draw this together, it's going to go yoink, 10, yoink, 6. I think, oh, and the resultant is always from the tail of the first to the tip of the second. Here's my force resultant. How can I find the magnitude? Hey, that's a lovely right angle. This is like a job for Pythagoras. Find the magnitude on your own, please. 10 squared plus 6 squared square root. Do you get a magnitude of 11.66? Newtons. I guess I should write down Pythagoras. 10 squared plus 6 squared equals FR squared. That's enough. I'll clue in from there. Oh. At Go look and see where your resultant is coming from, where it's starting from. Find the nearest side to that. That's the angle that I want. I'll call that angle theta. By the way, that angle there is going to be what of what? North of south, east of west, what of what? Let's see. Start out going east, drop down south, and you get to there? South of east. I'll leave a little space for the angle. South of east. How big? Opposite hypotenuse. Oh, it's kind of nice. Which trig function? Opposite hypotenuse, Mr. Dueck? How about try that again? Opposite adjacent, Mr. Dueck. Sheesh. Sheesh, Mr. Dueck. Which trig function really, Mabad? Tan. Tangent of what always goes next to the trig function? The angle. What's the angle this time? So, it's a variable. What do we call that there variable there? No. Theta equals opposite, yoink, over adjacent, yoink. How do I find an angle? Second function tan, right? Shift tan. Shift tan of yoink over yoink. You get 31 degrees. 31 degrees south of east. Example 6. A plane is flying due north at 132 meters per second. A crosswind is blowing due east at 44 meters per second. What's the plane's velocity relative to the ground? What would the tower on the radar see the plane traveling at? The plane feels like it's pointing due north, but unbeknownst to it, it's also getting pushed sideways in a side wind. Well, here's our argument. The velocity on the ground is going to be the velocity of the engines combined with the velocity of the wind. Say what? If this is the airplane and the engines are pushing it straight ahead, need some more room, Mr. Dueck, to get this out in the open. If my chair is an airplane and its engines are pushing it straight ahead, but there's a side wind pushing it sideways, it'll be traveling kind of like that. It's pointing that way, but it's moving diagonally. Is that okay, Haley? Okay. Let's draw a picture. Dalp. I don't know what the ground velocity is going to look like, but... Oh, engine. Yoink. 132. Plus. Crosswind. Alexis, crosswind which way? How long should I draw the 44? About 1/3 as long as that if I want to be a nice scalish diagram. So I'll go about there. 44. Alexis, how do I add two vectors together? Draw them. (132) plus 44. The resultant is going to be that. It's going to be that. This is going to be the velocity with respect to the ground, what the people on the ground see. Good. Find the magnitude. How can I find the magnitude? Looks like a job for our old friend Pythagoras. 132 squared plus 44 squared, square root of that. Get 139.1? 139.1, Mr. Dueck, meters per second at direction. Hey, there's the angle I'm going to find where my resultant starts. That angle is going to be what of what? South of north, east of west? What of what? Starts out going north, and then it tilts west of north. Right? East of north. That's what I said. East of north. So leave a space for the degrees, but it's going to be east of north. Now let's find the actual degrees. Opposite, adjacent, or hypotenuse. Opposite, adjacent, or hypotenuse. Adjacent. Which trig function? Tangent again. Thank you. Woohoo! Jaron, what always goes next to the trig function? And what's the angle this time? It's a variable. Theta, did you say? You said theta, yes? I gave you an out. You should have said, yes, Mr. Dueck. Absolutely, I said theta. What? Can't you hear me, Mr. Dueck? Jaron, equals what over what? I'll give you a hint. It's either 132 or 44, or 44 or 132. What over what? Yes. How do I find the angle in my calculator? Second function tan of that fraction in brackets. Second function tan, inverse tan of 44 divided by 132, putting everything in brackets, and I get an angle of 18.4 degrees. 18.4 degrees. How do I add two vectors together, Ronnie? Draw them tip to tail. How do I add two vectors, Kiana? Draw them tip to tail. And then what of what? Turn the page. Have some vector practice for you, but I also got a kind of a cool video to show you. So hold on. So, homework number 1, 2, and 3 from the handout. And then, if you want to take a look at this sheet here, which is called Vector Addition Practice. Okay? Eventually, we're going to be doing more, but for now, you can do number 1. Okay? These ones are a bit tricky, but there is a hint, because now you're adding 3 vectors. It says, hey, add the vectors that are along the same axis first. Add your north-souths together, because you can do that in your head and make it 1 vector. Add your east-wests together, because you can do that in your head, make it 1 vector. And now you're adding 2 vectors. How do I add 2 vectors? Draw them tip to tail. And do some trig. Components we can't do yet, because I haven't showed you components. But you can do part B number 2. Now take a look at 2D. If you draw a very, very, very careful diagram, you might be able to do 2D. Who's in pre-calc? Has anybody done the sine law and the cosine law in pre-calc yet? Okay, so 2D I'm going to cross out temporarily, but don't cross out the question. I'm just not assigning it yet. Foundation students, if you draw it, you should get a triangle that you can solve, but it won't be a right angle triangle. When you draw it tip to tail, you have to use the sine law or the cosine law, which, remember me always saying, hey, we use this in physics all the time. We do. So you know what? Put a star next to D. Not yet. Put a star next to E. Not yet. F is overkill. G is overkill. You can cross out F and G. There is a way to do D and D without the sine law and the cosine law, for those of you who haven't seen the sine law and the cosine law. And that's what I'll be showing you next class. It's called breaking it up into components. Okay? So 1, 2, and 3 from the handout with the notes, and then 1 all under practice problems, vector components. Not number 1 yet. That's going to be next class. 2 is fine. Put a star next to D, E, and G and H. Sorry, D and E, F and G. You can nuke completely. Hang on 1 second, please. Right click. Stop.